Swayam Prabha. Digital India. Educated India.
So good day to all of you. We've been discovering and talking about liners for the last 3 lectures, I think. And today let us wind up the discussion on liners for landfills. Let's wrap it up in a nice comprehensive manner. A brief recap. We've been discussing about this concept of a composite barrier which has a geomembrane at the top in intimate contact with a low permeability clay, a thin element and a thick element. And we started discussion on the thick element, the compacted clays and the amended soils last time. And we said typically at a site we'll have 4 options: use the in situ clay if it is available, excavate and recompact. If clay is not available, we'll have to import it from a nearby area. If that is not the case, we can amend the local soil by adding 5 to 15% commercial bentonite to it, and the permeability will typically fall below the required level. Or you may have to import a clay from a far-off area. So the steps typically are to identify a borrow area from where the clay is going to come. Suppose you have a borrow area, but the clay is still not having permeability less than 10 to the power of minus 7 centimeters per second because it is clay silt, then you can bring it from the borrow area and still do the amended soil. That means you still add the commercial bentonite to it, and then you will get the permeability. So you have to perform laboratory tests and then you have to construct. So the laboratory tests which we talk about are classification of the soil, grain size distribution and plasticity, compaction, the standard Proctor test we have done in the lab, and the modified Proctor test, and the compaction test on soil plus commercial clay. Now the difference is in soil plus commercial clay, every time you add the clay, the compaction curve changes. Why? Because the grain size distribution changes. So the OMC will change and the MDD will change. So we have to perform for all the range of additions. In fact, we should start from 0, original soil, 5, 10, 15, 20%. And then we have to find the permeability, and this is the critical parameter. And do understand that when we talk about permeability of less than 10 to the power of minus 7 centimeters per second or 10 to the power of minus 9 meters per second, we are talking about the saturated permeability and not the permeability of the unsaturated soil. So critical to doing the permeability test properly is the fact that we must be able to saturate the sample, and we must be able to prove that it is saturated. If I think I have saturated a sample, but it still has got air in it, it's going to give you a lower permeability, and you are going to feel very happy that you have got a soil which meets the permeability requirement. So we look at this a little more carefully, and after that we can do strength and compressibility. Now here a word is used, flexible wall permeameter, which we have not used in the undergraduate class, and a rigid wall consolidation cell permeameter. Most of us have done the consolidation test, and we can get the permeability from the consolidation test either indirectly by computing CV, coefficient of consolidation, or directly by permeating the water. So we are going to look at these two a little more closely. But first let us examine whether with your current knowledge, how would you perform a test on a low permeability material, and how would you ensure that it is saturated? So which tests have you performed in the undergraduate days, or at least theoretically you know about them? The falling head method and the constant head method. So which method do you use in clays or in fine grained soils? So we use the falling head method. Constant head method is not used, but falling head is used. So this is used for fine-grained soils. Do you remember how you did this test? How did you prepare the sample? The sample must represent the field condition, right? We are finding the permeability of a compacted clay liner. So it is going to be compacted. It is going to come from a borrow area. We are going to compact it in layers. So we have to do the same compaction in the laboratory. And having done the compaction, then we have to perform the permeability test, right? So which compaction test will you do in the laboratory, or did you do in the laboratory when you did your undergraduate test? And how did you do the permeability test? Anybody has done the permeability test in their undergraduate lab? The falling head permeability test? Well, it's an essential requirement to get your bachelor's degree that you should know how to do a permeability test in the lab. Okay, conceptually you know how a falling head test is done. So how is the sample prepared? How do you prepare an as compacted sample? I can take the soil, I can take the OMC or the water content at which I am going to make it in the field, and I can compact it in a compaction test. So I can compact it in a Proctor mold. So now I have a Proctor mold full of soil. And how do I do the falling head permeability test? The falling head permeability test conceptually looks like this is the sample. You create a difference of head and see the rate at which the water falls, right? So anybody recalls this? How does this happen? There is you may have an arrangement where there is a thin tube at the top, and you may allow this to overflow. So this head is constant. This head may fall with time, and as it falls, you have a formula from which you can get permeability. Do you remember this? Well, this is one way of doing it. The other way, and the better way of doing it, is to push the water bottom up. Push the water bottom up. That means keep this higher and this lower. So the other alternative is, if I'm having the reason is, whenever you are trying to extract air from a sample, it's better to push the water bottom upwards, because air being lighter than water will come out at the top. You put water at the top and try and push air downwards, it resists being moved downwards. So this is another arrangement. But the main question is, how do you ensure that this is saturated? How would you ensure that your Proctor compaction sample is saturated? Any thoughts? Well, if you have clay and if you add water to it, in how much time will the water come out from the sample? How much time will it take to travel? How many centimeters is this? 10 centimeters or thereabouts? Water travels in clay at 10 to the power of minus 7 centimeters per second, which I have often said is some feet per year. So water comes out very slowly, doesn't take out, doesn't become saturated. If it was sand, you can say, I will flush the sand, I'll put the water from below and the air will come out, and because sand has got high permeability, water will come out in a few seconds or few minutes. So clay is difficult to saturate, and there are only two ways of doing it. And one is, how did you saturate your sample in the triaxial apparatus when you did the triaxial test? You've all done a triaxial test? You've done a CU bar, consolidated undrained triaxial test with pore water pressure measurement. So did you have to ensure that there was no air entrapped in the sample? Now how did you ensure that there was no air? I know, but if it is not equal, then what do you do? What was said was, in a triaxial cell, you apply a cell pressure, increase the cell pressure, and the pore pressure should increase by an equal amount. But if it does not, then how do you saturate the sample? Yeah, so the word is we do back pressuring of a sample. We force the air to get dissolved in water by putting extra pressure in the sample. So in a triaxial test, you are using back pressure to saturate the sample, and you use a parameter called the B factor. And how much should be a B factor ideally? Ideally it should be 1, because then that means delta change in cell pressure is equal to change in pore water pressure, but the acceptable level has to be more than 0.95. In fact, don't think 0.95 means 95% saturated. So you have to have a B factor very close to unity. So we can saturate a triaxial sample, but we can't saturate a large sample in the Proctor mode. In a consolidation test, we also saturate a sample. The size of the triaxial sample is 38 millimeters and 76. And does the shape of a consolidation sample, is it similar to that of a triaxial sample? You remember consolidation ring? What's the size of the consolidation ring? So the consolidation ring is like this. (20 or 25 mm), about 1 inch thick. How do you saturate a sample in the consolidation test? Anybody would like to say? Typically we say soak the sample, and soaking the sample might saturate it, but that's a misnomer. Once you immerse a sample in water, the water is at the top also and at the bottom also. The air inside cannot come out unless it is being forced under some gradient to come out. Air will not come out. So soaking a sample does make the degree of saturation go up, because water is in contact with the lower surface and with the upper surface, and some of the suction, if there is negative pore water pressure, will draw in the water, but does not necessarily saturate it to 100% to get a B factor of 1. For saturating a sample which is in a consolidation ring, you have to have contact with water only on one side and leave it open on the other side so that the air can come out. And in clay, you remember there is a capillary fringe. In clay, if you have a groundwater, then a capillary fringe is formed above the groundwater. Do you remember the magnitude of this capillary fringe? How high can this capillary fringe be? Few millimeters, few centimeters, few tens of centimeters, few hundreds of centimeters. 10 meter is huge, but a few meters. So you can have capillary fringe a few meters. That means clay tends to suck in the water because it has got, if it is partially saturated, it has got a suction, and the suction draws up the water, and due to surface tension, the water rises by capillary action. So just if I take this sample and put it in a bowl of water, there's a porous stone at the bottom. This is the clay sample. It's in a consolidation ring, and I fill this I don't submerge it. I don't soak it in underwater. What will happen? Water will be pulled up and air will be pushed out from the top. And our experience shows in the laboratory that this is going to saturate the sample. But you have to keep on checking the water content and keep on checking the degree of saturation. Okay? So, let's look at what are the ways we test this in the laboratory. So, I use what is called a flexible wall permeameter. The flexible wall permeameter is a permeability test which is done in the triaxial apparatus. Okay? The triaxial cell, the same soil sample, stage 1 is identical, you saturate it by back pressure as in a consolidated undrained test with pore water pressure measurement. But now instead of shearing the sample by putting a load on it, I cause a head difference between the two sides of the sample. And water will flow from in the bottom upwards. And as the water comes out from the top, please remember you had a loading cap on the top. And the loading cap did not have a hole in it through which water could come out. But in this case, you use a loading cap through which water can come out. So if I was to make a diagram of the triaxial sample in a, you have your porous stone here, you have the porous stone here, you have the loading cap here, and there's a hole in the loading cap. Okay? And this is attached to the pedestal of the triaxial cell, you recall that? And this hole can also have a pipe which is attached to the base pedestal. And this can come out from one of the 4 valves at the bottom. So I do everything identical to the triaxial test except that I cause a head difference and I make water to flow through a sample with B factor equal to 1 and measure the volume change with time. Measure the volume change with time. So there's a differential in head at this point and at this point. And that difference in head is applied by the cell pressure application and the pore water pressure application system. So I can create a small head and measure the amount of water coming out, and this is called a flexible wall permeameter. So the concept is identical. You can read up more about this, but why is it called flexible wall? Because it has a rubber membrane around it. It's not a rigid wall like a consolidation ring. So you have a membrane around it, and that's the flexible wall. The membrane prevents side wall leakage. The other test is the consolidation test, in which, if you look at this diagram, we can flow the water from the bottom of the sample through the sample and out of it, right? So I can attach a burette here, and create a head. So if I go back to my diagram here, I can attach water to flow under a head, and I have a porous stone and I have a loading cap, if you recall, then I can get the water to come out. But this will be done like a falling head test. So the water level will be increased by us to this level, and this will allow overflow, and my head will fall with time, and the flow will occur bottom upwards. So you can use a direct measurement in a consolidation cell, but this is a rigid wall permeameter. Rigid wall because the ring is rigid, and this is a flexible wall permeameter. So the Testing which is done in the laboratory is in a flexible wall permeameter and a rigid wall permeameter, and the size of the sample has nothing to do with the Proctor compaction mode. Saturation is the most important aspect. So remember, apply back pressure in the flexible wall permeameter. B factor should be close to 1. Consolidation sample is by immersion, not by soaking. Immersion means you will have water at the lower surface but no water at the other side. So it's partial immersion of the sample. Partial immersion of the sample. Inadequate saturation will give you low K values, and those results will be erroneous. Side wall leakage will give high K values. Now, just imagine that I put some cement concrete in the consolidation ring, okay, and I do a permeability test. After the rich cement concrete has set, I get some water is coming out. One of the problems with a rigid wall permeameter is there can be leakage between the smooth wall of the ring and the soil or the impermeable material. So we have to be very careful that side wall leakage does not occur. And how do we ensure that? We have to apply a normal stress on the sample so that the soil pushes against the walls of the ring, and we must not forget to apply the, what do you apply on the inside of a consolidation ring? Silicone grease. That is, will prevent the water from passing along the side wall. So side wall leakage is an important aspect. And I have to change this immersion to partial immersion, so let me try. So once you have done this, what do we see? I will have to do these permeability tests at different points along the Proctor curve to see how the permeability varies with the water content. So this is the standard Proctor test, this is the modified Proctor test. So I may take 5 samples, 1, 2, 3, 4, 5. And when I have these 5 samples, then I can get the permeability values, and this will show you that the permeability will decrease with water content. This curve has lower permeability than this, so this corresponds to the modified Proctor test. This is for the standard Proctor test. If this is 10 to the power of minus 7, I know that I should compact wet of this point to get that permeability. When I am using an additive, my compaction curve will change with the amount of additive. So I cannot predict in how it will change, but I can get these different curves. And then for each curve at a given prescribed water content wet of the optimum, I can find the permeabilities, and I can get a plot of coefficient of permeability with the percentage additive that I have added. And again, this will give me how much is the additive required for getting the permeability. And this we have already discussed earlier, we should preferably be on the wet side of the optimum. And here it shows that in Delhi silt, which was sandy silt, we added 3 types of additives: bentonite, kaolinite, and a local clay which comes from near Roorkee. It's called Dhanori clay. So the round symbols show how the permeability decreased with bentonite, the dark symbols show how it decreased with kaolinite, and this shows how it decreased with Dhanori clay. So if you are going to add bentonite, 5% is sufficient for the purpose of getting low permeability, but it must be mixed very well, and you will need higher percentages of the other material depending on its plasticity. So in this way, I can find out the additive content. Then I have to construct the clay barrier. We've done the lab studies. So we identify the borrow area. Suppose I'm only using a compacted clay barrier, then I adjust the water content in the borrow area. Suppose the soil is totally dry, I can do some sprinkling there so that it's close to the optimum moisture content. We excavate it and transport it. At the landfill site, we level the landfill base, we unload and spread the clay. We are going to do 4 layers of 25 centimeters thick. We do some spraying of water and mixing. This is final adjustment. For example, let us say that your optimum moisture content is about 28%, right, for clay. You want to compact it wet of optimum 1%, so 29%. In the field, at the bottom area, the soil has got 4% moisture. It's dry. So you will bring the 4% moisture to 20-25% in the field by sprinkling or irrigating that soil. When you reach your site, then you will make the final adjustment from 25 to 29 because then you have to add a little bit of water. If you bring it to the site and start adding a lot of water, water may form a slush with the soil and it may create a problem. So only final adjustment is done on the site. We will do compaction using sheepshoot roller and then place the next layer, and after the 4 layers are over, we will do final smoothing with steel drum roller. And then as soon as the final smoothing is done, we have to place the geomembrane on the compacted clay liner so that the liner clay does not become dry and desiccate and you don't get shrinkage cracks. And further, we should cover the geomembrane without delay with a protector so that no damage takes place to it. So advantage of using sheepshoot roller, you can use heavy rollers with protruding feet. You get kneading type of compaction which breaks down clods. The kneading action has some mixing action also, so water gets mixed properly. And take a clay sample 25 centimeters thick, you put some water on top and you run a smooth steel drum roller on it. The water will not even penetrate properly into the soil. You will have to use some disc harrows. You can try that. But here, while the sheepshoot roller is moving, it is making pock marks and the clods are breaking and the water is mixing properly. It allows you to have proper bonding between the layers and compaction is from bottom upwards. You can also use pad foot rollers, which are smaller protruding feet than sheepshoot rollers, and, but they are not as effective than the sheepshoot roller, but they are better than smooth steel drum rollers. So please do remember that you are going to have 3 or 4 layers. They should be properly fused. If they are not fused properly, then you will have these horizontal zones of high permeability. The sheepshoot roller actually compacts bottom upwards. When the soil is loose, you will find the whole sheep's foot sinks into the soil. As you do the number of passes, the sheepshoot begins to walk out. It begins to rise because the lower portion is properly compacted. This is quite opposite to what happens in a smooth steel drum roller. When you move the roller, the top one gets compacted first, and the lower layers do not become that dense. So this is the way you have to use the rollers in the field for compacted clay liners. The critical thing is, how do you compact the clay along the slope? Both options are available, but mostly this is a better way to do it. Because it's very difficult to move the rollers. Typically your side slope will be 3:1 or 4:1. To be able to move a roller along that, a dozer can move with a good drive, but a roller is difficult to move along a slope. So you will be compacting in horizontal layers. And remember, if your bonding is not proper, then you are creating zones of high permeability in the horizontal direction. So it's critical that your fusion is good, and that's what a sheep's foot roller does. So the thickness of this clay is 1 meter. So the question asked is, how can I compact a 1 meter thick clay? My roller is 2.5 meters wide, right? Well, do remember, first you have to use smaller rollers, but this is 1 meter thick. If you look at a 3:1 slope, this will become 2 or 3 or 3.5 meters wide in a horizontal sense. The thickness when we talk about is normal to the slope. So this is, when you cut it horizontally, will have a much wider thickness, and it is possible to do this compaction. If you are constructing with amended soil liner, now this is a little different process and you should know it. You will excavate and pulverize the local soil. The very important thing is pulverize it. Then you will get your commercial clay in cement bags. As I said, you can get bentonite in cement bags. You have to mix in a dry state in a central mixing plant. So excavate your soil, it may be local soil or maybe coming from 5 kilometers. Crush it and pulverize it so that it becomes like powder, fine powder, because you need intimate mixing. Just remember, you're going to add 5 to 10% bentonite. If there are clods, if it is not dry, it is sticky, then that 5% bentonite will get concentrated in one area. It won't mix. But if it is finely ground and it's like powder, and you have the bentonite powder, then like cement will mix with soil in its dry pulverized state. That's the way it will mix. So mix in dry state in a central mixing plant. This is like a standard batching and mixing plant of a, say, a concrete production unit. Add the water after the dry mixing is complete so that there is well spread out bentonite in the entire matrix. Add the water and mix in the plant, then you transport and spread and compact in the same manner. It says here, avoid in-place mixing of soil and commercial bentonite. I had shown you a slide program where they were doing in-place mixing. They were working very hard at it. But the issue is how many clods were they breaking and how much effective would that be. So if you're going to do in-place mixing, please use more bentonite. I would say then instead of 5 to 10%, you're going to be operating in 15% plus range, because you will not have that much homogenized mixing of in-place mixing. I don't normally agree with in-place mixing of soil, but it is cheaper. People tend to use a tractor and plows and harrows to do that. So this is the setup. If you see, you can store your bentonite in a silo. You can also have a soil bin. This is your stockpile of the soil which has come from the borrow area. It goes into a soil bin where you might be crushing it further or pulverizing it further. You do weigh batching, you weigh batch, you have a mixer. First you mix the additive and the soil in dry. Then you add the water, and then you have the amended soil, put it in a truck and send it for compaction. And you have a rigorous testing program. What kind of quality control tests must you do? So typically you will see that you have to do grain size distribution, Atterberg's limits, water content, compaction, laboratory permeability tests, in situ density, compaction control, in situ water content, and laboratory permeability on undisturbed samples. How often do you use it? 1,000 to 5,000 cubic meter. One set of tests. It's not one test. Please understand, if you are going to find the permeability of a soil, one set of tests may mean 3 tests. Why? You are not so sure. You're getting a little bit of variability. So one set of tests per 1,000 cubic meters, per 5,000 cubic meters. And of course, for compacted soil, it is per square meter, 500 square meters of the compacted layer. So this kind of a quality control program will be prescribed. This is for just compacted clay without additive. If you have an additive, that is if you have an amended soil, then you have to do a lot of testing at the plant. You have the original soil, you have the additive tests. So first do the original soil test, additive, then do the mixture, testing of the mixture, and then of the compacted soil. So here also it's 1,000, 1,000, 1,000, 2,500, that kind of a sampling program. So with this, we've looked at the thick element now, how to construct the thick element. Not easy, requires quite a precise field construction and strict quality control. And therefore, one is always looking at an alternative to this very intensive field construction activity. Now we look at the thin elements, and we look at geomembranes and a new set of barrier material called GCLs, geosynthetic clay liners. I'll come to that. But our next discussion is on the thin element at the top. Geotextiles you will do in your course on geosynthetics. I've only said 2 things, a protector or a filter. Typically, non-woven geotextile, more than 400 grams per square meter. But why is it non-woven and not woven? Why it is 400 and not 200 or 600? This will come to you from your course in geosynthetics. So, just to recall, geomembranes are relatively thick polymer sheets. Typically in a landfill you will find them to be 1.5 to 2.5 mm thick. For very high landfills they will be 2.5 mm thick. They are flexible. When I say flexible, how much will they elongate before they break? So if you do a tensile strength test on a HDPE geomembrane, before it yields or breaks, it will have 50% elongation. Just compare it with soil. If I have a stiff clay, what is the failure strain? Strain at failure or strain at yield or strain at break. And if I have soft clay, or if I have loose sand and if I have dense sand. And so in dense sand, if you do a triaxial test, where will the failure come? At what strain? Pardon? 12 to 15% is for loose sand, and for dense sand? Yeah, it's low. You remember, in dense sand, the stress strain curve will look like this. You can have this behavior, or you can have this behavior. So this is stress, this is strain. And we said that in soils, in dense sand or stiff clays, this may be 3 to 5, and this may be 10 to 15. So where is the failure strain for an HDPE geomembrane? If this is 15, this is 30, this is 45, this is 60, and this is 75. So the range that we are talking of, HDPE will have failure in that range. It can be also 100%. 50 to 100% is the elongation before a geomembrane fails. So it's a flexible material. Even if the base settles a little bit, it's not going to rupture or fail in tension. It's going to have that flexibility. And if you want even more flexibility, then there are other materials which are like VLDPE, LLDPE, low density polyethylene, which instead of failing at 50 to 100% would fail at 200 to 300%. But they will not be that strong. So it is going to be a playoff between flexibility and strength. So maybe which has more settlement, cover or liner? A liner has more settlement because the stresses are higher, but a cover has more settlement because there is biodegradation. So in municipal solid waste landfills where the biodegradable content is higher, there cover settlements can be very large. But if you have inorganic waste which does not settle due to biodegradation, then maybe the liner settles more. But if you are going to have very large settlements, then you will use LDPE polymer. Okay, so they are relatively thick, they are flexible, they have significant strength, they are heavy. We talked about 400 GSM for a geotextile, but here we are talking of 1000 to 2500. So a lot of polymer. They can be smooth or textured. I showed this to you last time. And they will have resistance to puncture and tear. They can have strong welding of seams, almost the same strength as the parent material. When you weld something, you are always bothered. You have used thermal welding or you have added something. Is it as strong as the parent material? So in HDPE welding, you will see what is the quality control criteria. They have ultraviolet stability. Most of the time they look black because ultraviolet stability comes in polymers when you use carbon black. Carbon black gives you UV stability. So many of the overhead water tanks and many of the polymeric materials which look black are on account of UV stability. They can come in wide rolls, 7 meters. Now they are talking of even 10 to 12 meter wide rolls. So 10 to 12 meter wide is 30 feet. That's the width of your drawing room perhaps. So you can get very wide rolls, and the rolls can be as long as 100 meters. So that's the football field. So these can be rolled and they'll come in a truck. To minimize the joints, the wider, the longer, the less the joints. They are resistant to most chemicals. Other than HDPE, there are VLDPE, LLDPE, PVC, PET, but most popular is HDPE for liner. And if I look at this table, I will not go into details, but just like we test soil, grain size distribution, density, specific gravity, plasticity, water content, strength, compressibility, permeability, there are a series of tests which have to be performed on geomembranes. Thickness, tensile strength, tear resistance, puncture resistance, density, melt flow index, carbon content, brittleness, environmental stress cracking, seam strength, dimensional stability, interface shear, waste to geomembrane compatibility. Some of these are routine, some of these are special tests. But just to get an idea, a 1.5 mm thick geomembrane will have 18 kilonewton per meter as its tensile strength. And it will have some tear resistance and some puncture resistance, and this is the requirement from the point of view that it should not be damaged during installation. The tear resistance and puncture resistance has very little to do with design. These are durability tests. It will normally have a density of the order of 0.94 grams per cc. Carbon content must be more than 2%, and seam strength must be greater than 90% of the original material. This is a requirement. Seam strength in shear and seam strength in peel, which is totally different, should be 60% of the parent material, and we'll have a look at this later. So there's a full gamut of tests which the geomembrane must meet. What you have to do before you lay a geomembrane is to prepare, basically, if this is the base of the geomembrane, of the phase in which you are going to put the cell. Suppose this is a below ground landfill, this is the base, and this is at ground level. So it means the ground is sloping like this and like this. You have to prepare a panel layout map. How are you going to unroll your geomembrane? Where are the welds going to be? So it shows that one roll will be like that, one roll will be like that, and depending on the lengths and widths, you will have these joints which will be welded together along the slope. So prepare a panel layout plan. Installation should preferably be by the manufacturer or his installer, because how are they going to join it, how are they going to seal it is a specialized job. Store the rolls in a dry protected area. Movement of rolls requires a light loader or a forklift. Unrolling should be done at the site. Spotting and unrolling should be as per the panel layout plan. Before unrolling, it should be ensured that the clay surface is smooth and all lumps, stones, protrusions, roots should be removed if there are any which are coming with the borrow material. Minimum overlap required for seaming is to be provided. When two of them have to be joined, they don't join like this, they have an overlap. Wind tends to blow this geomembranes and displace them. So you will find a lot of sandbags are required to prevent uplifting by wind. In India, a lot of old tires are put, you will find in some photographs. And then thermal fusion of seams. Many types of welds are there. We prefer the dual hot wedge. Very important is there will be some pipes which will be passing through the geomembrane. And that, how do you weld the geomembrane to the pipe? Those construction details have to be given by the manufacturer and have to be with strict quality control, they have to be ensured. Geomembranes are anchored at the top of side slopes. If you put a geomembrane on a side slope, it tends to slip down. So there will be an anchorage in a trench at the top. Geomembrane should be covered with the soil or the protector immediately after installation. Soil should not be dropped directly onto the geomembrane but pushed forward. In India we do this manually, but in developed world they use light crawler mounted loaders and they push this forward. All staff should wear tennis shoes and not heavy construction boots. Installation should be done during the coolest part of the day when the geomembrane has not expanded. Otherwise there is a thermal expansion coefficient of the geomembrane and they can become longer during the daytime. So I only showed you the plan layout of a geomembrane panels and where the seams will be made. And these are some of the type of welds. These are extrusion welds. You are putting extra material on the overlap or in between. And these are thermal fusion welds. So the weld which is done in most geomembranes is this one. It's called a dual hot wedge weld. You weld it in such a manner that there is an air gap at the center. And basically just heat it and weld it. Now, when you have an air gap at the center, please remember, suppose you have a 100-meter roll and the two geomembranes are going overlapping and a weld is being created like that. So you are creating a tunnel. So the good thing about the tunnel is you can check whether it is leak proof or not. If this weld and this weld is good, if I put air pressure in it, it's going to, the air pressure will not be dropped like in a cycle tube. So that's the test. One test for a full length of the roll along the dual hot wedge weld. You apply air pressure, keep it for a few minutes. If the air pressure is sustained, it means there is no leakage. Two types of tests are done for seam strength. If this is the welded portion, we are doing the shear strength test, pulling the two membranes in this direction. So there is shear along this face. This must be having the same value as 90% of the parent material. So the shear strength in this test should be 90%. This is the peel test. You try and peel apart the joint. And this is, most of the stress situation mostly is like this. But here also you should have 60% of the strength of the parent material. So these are the two seam strength tests which are done in the field. And as I told you, the geomembrane has to be anchored at the top, otherwise it has a tendency to slip down. If this will not slip down when you put soil on top, that will have a tendency to make this slip down. So either the geomembrane will go into a trench, or if there is sufficient horizontal distance available, it will be run out horizontally. So these are the two ways in which you can hold the geomembrane in position. Just like there is quality control in soils, there is quality control in geomembranes. But before I discuss this, is there anything that you would like to talk about regarding geomembranes?
Regarding that air tunnel in the wedge.
Yeah. Yes.
There is a probability of puncturing in that.
There is a probability of
Puncture or tearing of along that air tunnel.
So the question being asked is, if you are doing the welding, dual hot wedge welding, and the two rolls are going like this, and I am welding like that, and I apply air pressure and I find that the air pressure is not sustaining itself. So how do you find a leak? How do you find a leak in when your cycle tire is punctured? You put it in water and bubbles will come out, bubble, 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 right? Well, here you can't put the two geomembrane in water, but you can take a soap solution and you can put the soap solution along the joint, and you can apply the pressure, and wherever there is a leak, that soap solution will form bubbles. And sealing it is no problem because you heat it and it is sealed. The polymer, how is the weld made? It is just two hot points which are running across, they seal the thing together. So once you have got the leak, you can do a patch weld, you can put an extra patch, and you can heat it, and just like a puncture, this will be sealed. The only thing is locating it, for which typically a soap solution is used. Okay? Any other question which is coming to your mind? So we have quality control in geomembranes as well. You must have a proper contractor who's supplying the geomembranes, has been doing projects for 3 years. You will do the tests on the rolls as received before they are installed, and then you will do the tests on the field installation. Some of them will be destructive testing and some of them will be non-destructive testing. So typically one set of tests per 5,000 square meter is what you do the testing, and one set per lot. I mean, if geomembranes are coming to you in different lots, then you do one set per lot, which may be less than 5,000 square meter. But at least 2 sets for each yearly phase, and not less than 5 sets for the entire landfill. Field trial seams test strips of 1 to 3 meter in length. You will construct these seams or these joints on some leftover pieces, spare pieces of geomembrane. You will construct this, and then you will do the shear and peel tests. You will also do destructive testing of field seams. Actually, when you have installed the seam, you will cut out portions and you will do field testing, and you will a new patch is installed to close the hole which is created, and there are certain number of tests which are prescribed. As I said, 100% non-destructive testing. Every joint in the dual hot well seaming, air pressure of 200 kPa is applied within the seam for 5 minutes to check for leakage. The pressure must sustain for 5 minutes, and a soapy solution can be applied to the seam with a vacuum chamber sometimes to see whether there is any leakage at a particular point within 15 seconds. So there is a destructive testing procedure and a non-destructive testing procedure for the geomembranes. The last material that I'd like to talk to you is about geosynthetic clay liners. Now, why is it that geomembranes, which are almost impervious, are not good as standalone material? Because they can have tears and punctures. What if they were self-healing? That means you had a tear and a puncture, but as soon as they had access to water, they would swell and self-heal themselves. So a new generation of materials called geosynthetic clay liners has now been developed, which are thin, factory made, but are self-healing. So before I look at that, you have 2 geotextiles, and if you place clay between them, you get a GCL. And how much clay? Only 5 millimeter clay. 5 millimeter? Less than 1 centimeter thick clay. That sounds great. The only question is, how do you put the clay between this? How do you ensure that the clay doesn't move from one side to the other? And how do you ensure that it has the permeability of a 1 meter thick clay? So if I have 1 meter thick clay and my permeability is 10 to the power of minus 7 centimeters per second, right? And if I need a 10 millimeter thick clay, what should be the permeability of that clay? 10 millimeter clay is 1/100th of the 1 meter thick clay. Therefore, the permeability of a 10 millimeter thick clay should be 10 to the power of minus 9 centimeters per second. And we do have a clay which has permeability of 10 to the power of minus 9, which is sodium bentonite. This is commercially available clay. So the concept is to put clay inside to geotextiles and give you a roll. And what's so great about a geomembrane? It comes in the form of a roll. I can just roll it out. I don't have to get a compactor, I don't have to mix, I don't have to pulverize, I don't have to do so many things. So the geosynthetic clay liner can look like this, 2 geotextiles with clay and adhesive. Maybe the adhesive will change the permeability. That is something which you may like to do research in. Sometimes they'll do clay plus adhesive plus some stitch across the two faces, or you can have it needle punched. That means you can have a lot of fibers which are punched in it, which gives it some holding capacity for the clay, and you can have a geomembrane plus clay. So these are the various kinds of GCLs. I'd like to show you a sample so that you just get an idea. We did the geomembrane last time, and then we said it can be smooth or textured. You remember this? And I showed you it had a shining surface, and the shining surface reflects like a mirror. And then we talked about a textured geomembrane, and also this also had a roughness. And then I talked to you about a geotextile, a blankety material. Well, this is yet another geotextile, probably more like 400 GSM. And now I'd like to show you a GCL. This looks like the non-woven geotextile on the top. I flip it around. This is a non-woven or a woven geotextile at the bottom, or a hybrid. Between the two, if I look at this, this is stitched together, but between the two is bentonite powder, right? And it's about 5 millimeters thick. This is one type of material. This is another one, non-woven geotextile, a geomembrane, smooth geomembrane, and between them bentonite. You are always bothered that if I put it up like this, will the bentonite come to one side, because it's a powder. So it is either stuck, or it is needle punched, or there is some stitching across which holds the material in position. So these are new materials which come in rolls and which can be rolled out. So commercial sodium bentonite sandwiched between or glued to geotextiles or geomembranes with K 10 to the power of minus 9 to 10 to the power of minus 12 meters per second, 10 to the power of minus 10 to 10 to the power of minus 12 meters per second. Advantages: they are factory made, clay plus geosynthetic liners, available in the form of rolls for easy installation. They have self-healing properties. The manufacturers say that if you put a pin through them or a needle through them, and when you remove the needle and when you saturate this, the bentonite will swell and self-heal. They are very thin, and hence if you use them to replace the clay, you will get 1 meter more of space to put the waste in it, and they are easy to install. So they are now being proposed that one should use them in place of compacted clay liners. The European practice has not allowed a thick clay layer to be replaced by a thin GCL. In the American practice, one of the two double layers, in American practice there are, you remember, double composite liners. So if you have a double composite liner, one of the two can be replaced by the GCL, but one thick clay must remain in position, because it might be able to heal a pin prick or a needle prick or a screwdriver, but will it be able to heal a 10-inch, a large hole, 3 inches by 3 inches? We talked about small hole being 10 millimeters by 10 millimeters and a large hole being 100 millimeters by 100 millimeters. 100 millimeters is 4 inches by. So if it has a tear, the bentonite is not going to expand and heal itself. So they can't repair major tears in it. So geosynthetic clay liners, the experience show, they work well when hydrated properly. That means they must have been given adequate moisture to swell. Otherwise, air will pass through them and water will pass through them. Joints are by overlapping. They are no longer welded. They are by overlapping. Shrinkage can occur if they are allowed to dry out. Because of the bentonite, what is happening? Because of the bentonite, when it hydrates, its strength is very low. It's like a clay powder. So when you put it on the sides, it can have a failure. So it requires flat side slopes due to low hydrated shear strength of bentonite. Also, it is observed now from field results that bentonite tends to move downwards. There is internal erosion if the gluing and stitching is not proper. And definitely it is affected by cation exchange. Because it is sodium bentonite, if calcium chloride solution will go in, permeability will increase by an order of 10 to 100. So GCLs should not replace thick compacted clays in a single composite liner, or both the thick clay layers in double composite liners. They can be used for replacing one of the clay layers in a double composite liner. However, if you want to use this as an additional layer, you are not getting very good soil, so you want to have a soil with 10 to the power of minus 6 centimeters per second, and instead of mixing 10% bentonite in it, you say, no, I would like to enhance it by using the GCL. So can enhance liner performance as an additional barrier layer if CCL permeability is not low enough. So this is an area of intense research nowadays. They have been around for 5 years now, and there are definitely some good examples of their performance, but the debate about whether all thick clay elements can be replaced by thin GCLs is still going on. So with this, we just see some photographs of the liners. Just remember, you can see why damage occurs, what kind of shoes are being used, and this is that air pressure test which is being conducted. This is another site where non-woven protector over the geomembrane, but typically you should be able to see the seams. Can you see the seams? All across. This is where I told you what is the role of these tires, just to prevent the flying away of the geomembrane. And this is what's happening closure. This is the waste being covered with daily cover, and that's your geomembrane. And I couldn't get a better shot than this for you to see. I told you always that they are inclined so that the water comes to the one drain. This is just after a rainfall. And you can see all the water has come here. And this is where the leachate will be pumped out from. The other thing that you have to notice in all these figures is you'll see some wrinkles, right? And that is because the geomembranes expand during the day and contract during the evening. So wrinkles are an essential part of what we have seen. But if you don't place them well, that's a separate issue. For example, here you can see the geomembrane is not properly covered, so it will get damaged. And that is another site. So with this, we come to our end of our discussion on landfill liners. We are now better exposed to what is a composite liner, what are geomembranes, how are they joined, and how do liner systems work in landfills. The design components, so far we have only looked at minimum specifications. What is the thickness of the clay? What is the thickness of the geomembrane? And individual component design we'll do as we go along. Any questions you have? Okay then, thank you.